Hi everyone, I'm Mingkun Liu from Ocean University of China. Today my talk is about the retrieval of sea surface temperature from HY-1C COCTS. I will introduce the HY-1 series satellites at the beginning. The HY-1 series satellites is the first generation of marine observing satellites of China. HY-1A was launched in May 22. HY-1B satellite followed in April 27. HY-1C launched in September 2018, and HY-1D was launched in June 2020. And HY-1C and HY-1D satellites are the operational satellites. And HY-1E will launch in this year. One of the main payloads on board HY-1 satellites is the Chinese Ocean Color and Temperature Scanner, COCTS. The COCTS is a 10-channel whisk broom scanner, including 8 visible and near-infrared channels for ocean color measurements and 2 thermal infrared channels for observing SST. In this study, we focus on the HY-1C COCTS infrared calibration and the SST retrieval. There are 4 parts of my report, including the assessment of COCTS thermal infrared calibration, the Bayesian cloud detection of COCTS, the optimal estimation SST retrieval of COCTS, and the COCTS OE SST validation. Firstly, the assessment of COCTS thermal infrared calibration is conducted using the IASI onboard MetOp-B satellite as the reference instrument. IASI is a hyperspectral instrument with the capability of measuring the spectral range from around 3 to 15 micrometer with a spectral binding of 0.25 per centimeter. IASI is an excellent reference instrument for other instrument intercalibrations because the calibration of IASI is accurate and stable. This figure shows a demo of IASI measured spectral brightness temperatures for more than 8,000 channels with the spectral response functions of 2 COCTS thermal infrared channels. The red one is for the 11 micrometer channel, and the green one is for the 12 micrometer channel. The spatial resolution of COCTS is around 1 kilometer, and for IASI, the spatial resolution is about 12 kilometer. The calibration of COCTS and IASI are both based on the closed space and the internal blackbody measurements. The intercalibration methods include 3 steps. Firstly, the spectral readings of IASI are convolved with the COCTS 2 thermal infrared channels spectral response functions to calculate the reference readings corresponding to the 2 thermal infrared COCTS channels. Next, considering the spatial resolution of IASI and the COCTS are 12 kilometers and 1 kilometers from nadir, respectively, so that the IASI convolved and the COCTS readings are projected on grid of 0.12 degree, and then converted to brightness temperatures for the following comparison. The COCTS brightness temperatures are collocated with the IASI brightness temperatures. The spatial resolution of the matchups is set at 0.12 degree, and the temporal window is set as 30 minutes. In addition, to diminish the impact of the atmospheric path difference on the brightness temperature comparison, the threshold of the atmospheric path is set less than 3%. Thirdly, is about the filtering of matchups. Because the point spread functions of COCTS and IASI are different, The filtering of matchups located in the uniform scene is important because it will reduce the spatial uncertainties of matchups. Therefore, the homogeneity filtering of matchups is a necessary step. The relative standard deviation of COCTS brightness temperatures is an effective indicator to quantify the spatial homogeneity. These figures show the variations of the relative standard deviation of COCTS readings against it's about the COCTS minus IASI brightness temperatures against the relative standard deviations of COCTS readings. We can see that the dispersion degree of brightness temperature difference becomes significant with increasing RSD. So we set the RSD thresholds for 11 and 12 micrometer channels as 0.01 to select the matchups located in the uniform scene. Based on the filtered matchups, the COCTS thermal infrared BT were compared with the IASI. And this slide shows the comparison results. These figures are the global distribution of the brightness temperature difference, with the red panels indicating that the brightness temperatures difference against the latitude. We can see that the distribution features for these two channels are similar. The positive brightness temperature difference of COCTS minus IASI showed obvious dependence on latitude, with larger values in high latitude regions. In addition, the collocations are densely distributed in the high latitude region because of the orbital overlap of COCTS and IASI. These two figures are the brightness temperature difference against the IASI brightness temperature. It is obvious that there exists a significant BT dependence on brightness temperature. And this result is consistent with the global distribution. Overall, the mean difference for 11 micrometer brightness temperature difference is 2.68 K, and the standard deviation is around 0.29 K. For 12 micrometer channels, the bears is around 3 K, and the standard deviation is around 0.3 K. So after the comparison of COCTS brightness temperatures, we need to correct the COCTS infrared calibration. Considering the approximately negative linear dependence of the BT difference on IASI BT, so we used the linear robust regression to correct the COCTS brightness temperature. In addition, considering the matchup numbers are unevenly distributed against the latitude, the latitude-dependent correction coefficients are obtained. We divided the global region into 6 latitude zones every 30 degrees. Each regression was trained using the matchups in the corresponding latitude beam. Furthermore, the 2/3 of the matchups were randomly selected and used in the regression analysis, and the remaining 1/3 matchups are used for validation. Here are the comparison results after the correction, also including the global distribution of the brightness temperature difference, as well as the BT dependence. We could see that after the correction, the BT dependence were corrected, and the mean difference for the total matchups is around 0, and the standard deviation for two channels are around 0.2 K. So we can see that after the intercalibration, the COCTS brightness the accuracy of the COCTS brightness temperatures improved a lot. Next part is about the cloud detection. In this study, a Bayesian approach is applied for cloud detection of COCTS infrared brightness temperatures. Bayesian cloud detection is based on Bayes' theorem, determining a clear sky probability given the satellite observations and the prior background information. This is the equation to calculate the clear sky probability. We need to use the observation vector, including the COCTS observations of the two thermal infrared channels, as well as the local standard deviation for 11 micrometer channel. The background state vector includes the SST and the total column water vapor from the ECMWF ERA5 data. The background observation vector indicates the expected observation vector given the background state. This is simulated using the MODTRAN. So here are some results about the cloud detection. This is a demo in the ocean fronts. This figure is the brightness temperature before cloud detection. This figure is the RGB image of the reflectance channels, and this figure is the brightness temperature after cloud detection. We could see that the algorithm work well in the ocean fronts. And this one is a demo of daily brightness temperatures in global scale before cloud detection and after cloud detection. We will also validate the cloud mask performance using the retrieved SST evaluation results in the following parts. During these the figures, we could see that the cloud detection is giving plausible results and it works well in ocean fronts. The next part is about the optimal estimation SST retrieval of COCTS. The global COCTS global SST are retrieved by OE algorithm from July to August 2019. OE SST is the adjustment of the prior SST in the light of the difference between the observed brightness temperatures and the simulated brightness temperatures, assuming that the prior SST to be correct. For OE SST retrieval, SST is estimated through a weighted combination of the prior SST and the TCWV and the difference between the observations and the simulated BTs given the prior field. The covariance matrix of the prior and the satellite observation, as well as the prior information, are also necessary for SST estimation. A quality level on a scale 0 to 5 is also provided for each SST pixel. Quality level 5 indicates the highest quality. SST with quality levels 4 and 5 should be considered as high accuracy data. This figure shows the flow of COCTS quality control. The quality level are set based on the clearing probability, the chi-square value for OE SST, aerosol affected air, and also the SST invalid values, and so on. When we validate the OE SST, we choose the quality level of 4 and 5. Here is the comparison results of COCTS retrieved OE SST with iQuam SST. This figure is the histogram of the COCTS OE SST minus iQuam SST. And these two figures are the SST difference against the in-situ SST as well as the TCWV. And these figures are the a global distribution of SST difference for daytime and nighttime respectively. We could see that the SST difference of COCTS minus iQuam SST didn't show the SST dependence or the TCWV dependence. The overall statistics shows that the mean difference is around negative 0.15 degree, and the standard deviation is around 0.4 degree, and the RSD is around 0.33 degree. Compared with the COCTS level 2 SST products, the accuracy of OE SST improved a lot. We also compared the COCTS OE SST with IASI skin SST. The IASI SST data are provided from Australian Marine National Facility and the Ocean University of China. These figures show the MetOp-B geolocation. The comparison results show that the mean difference of COCTS OE SST with IASI skin SST is around 0, and the standard deviation is around 0.35 degree, and the RSD robust standard deviation is around 0.3 degree. So here is the conclusion. The assessment of HY-1C COCTS thermal infrared calibration is conducted using IASI as the reference instrument. The calibration of the HY-1C COCTS thermal infrared channels remains stable, and the accuracy is around 0.2 K after intercalibration. The Bayesian cloud detection algorithm is applied, and both the COCTS BT images and the retrieved SST validation distributions show that the cloud detection is effective for SST retrieval. The OE algorithm is used for COCTS SST retrieval. The COCTS OE SST are compared with buoy SST and IASI skin SST. The accuracy of COCTS OE SST is better than 0.4 degree. That's all. Thanks a lot for your attention.